Hi, it's Professor Adam. Let's talk about colligative properties. During winter, salt is often spread on roads to reduce ice buildup. It works by lowering the freezing point of water, a colligative property. When a solute is dissolved in a solvent, it will change certain physical properties of the solvent. These are called colligative properties. These properties include freezing point depression, boiling point elevation, changes in vapour pressure, and osmotic pressure. These colligative properties depend not on the type of solute added, but rather the total amount added. Remember that colligative properties are based on the amount or number of solute particles and not on the properties or identities of the solute molecules. This means that these solutions will have different colligative properties because they have different concentrations. But if the solute molecules have the same concentration but are different molecules, their solutions will not have different colligative properties, because colligative properties depend on concentration and not identity. In general, colligative properties arise because the solute particles interfere with the behavior of the solvent molecules at the interface between two phases. A liquid in a closed system will always have the same vapor pressure because solvent molecules at the surface will spontaneously enter and leave the liquid phase. The vapor pressure is determined by the number of gaseous molecules. When a solute is added, it can affect these properties because the solute molecules will occupy spaces at the surface, preventing the solvent from entering the gaseous phase. This decreases the vapor pressure of the solvent. The changes in the vapor pressure can be described by this equation. The new vapor pressure is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Modification of this equation, called Raouls Law, allows calculation of a useful parameter, the lowering of the vapor pressure as a function of solute mole fraction. The change in solvent vapor pressure can be described like so. And Raouls' law can be substituted in place of solvent vapor pressure to give a new equation. For a binary system of one volatile solvent and a non-volatile solute, the sum of the mole fractions must be 1, and so the initial equation can be rewritten as this. So the decrease in vapor pressure of the solvent is proportional to the mole fraction of the solute. The normal boiling point of a pure liquid is the temperature at which its vapor pressure is equal to 1 atmosphere. When a solute is added to a solvent, the boiling point is elevated. Solute molecules at the interface block solvent molecules from evaporating. As a result, more heat energy is needed to boil the solvent molecules. A simple relationship exists. The change in boiling point is equal to the molality of the solute times kBp, which is the molar boiling point constant. kBp is determined experimentally and has units of degrees Celsius per mole. Let's do an example. What is the boiling point elevation of 0.6 grams of sodium chloride dissolved in 50 grams of water? And we are given kBp of water. From our equation, the first step is to calculate the molality of sodium chloride, which is this. Then plug the values into the initial equation to get the elevation. And then, since the normal boiling point of water is 100 degrees Celsius, add the elevation to 100 to get the final boiling point of this solution. Going back to our initial example, salting of roads in water. When a solvent freezes, the particles must associate and form a lattice. But when solute molecules are added, this process is obstructed and a lower temperature is necessary to freeze the solvent. The equation to describe the depression of the freezing point is given as delta freezing is equal to the molality of the solute times the molar freezing point depression constant, which is also determined experimentally. The final colligative property is osmotic pressure. A dilute solution of glucose in water is placed in the right arm of a U-tube. The left arm is filled to the same height with pure water. Between the two arms, a semi-permeable membrane separates the liquids. Because the flow of pure solvent through the membrane from left to right, from pure water to the solution, is greater than the flow of solvent in the reverse direction, the level of liquid in the right tube rises. At equilibrium, the difference in pressure is equal to the osmotic pressure of the solution. This causes the flow rate to be equal in both directions. Applying an external pressure equal to the osmotic pressure of the original glucose solution to the liquid in the right arm reverses the flow of solvent and restores the original situation. Osmotic pressure is related to the concentration of the dissolved solute particles. It obeys a law which is similar to the ideal gas equation. Consider, for example, the osmotic pressure of a 1.20 mole per liter glucose solution at 298 Kelvin. The osmotic pressure would be 29.4 atmospheres. The osmotic pressure of a solution can have a significant effect on cells. Depending on the solute concentration, there are three types. An isotonic system has two solutions of equal osmotic pressure, and the flow into and out of the cell is equal. A hypotonic system means that the solution has a lower osmotic pressure than the cell, causing water to flow into the cell. And a hypertonic system, which has a higher osmotic pressure than the cell, causes water to flow out of the cell and into solution. Osmotic pressure is extraordinarily important in biology, biochemistry, and medicine. Almost every barrier between an organism and its environment acts as a semi-permeable membrane, allowing water to flow, but not solutes. The high osmotic pressure in foods such as jams and adobo help to dehydrate bacteria and preserve foods. Trees also use osmotic pressure, as when water evaporates from the leaves, this increases salt concentration in the tree and causes water to flow in through the roots. Let's check comprehension.